done down here, don't panic, okay? It's a lot of numbers, and I'll pass this to all of you, okay? So I'm putting values of mass, okay? And then I will put hold on, I'll tell you what I'll put. Hold on, I'm a bit lost over here now. Hello. Okay. So what you can do, again, I've not finished. I got distracted today. Okay. So given a mass of 9.072, if we put a damping of 200, okay, and we have a spring stiffness of 700, boundary condition, okay, you can see down here, boundary condition is 0.15 time is equal to 0. Velocity is equal to 0, time is equal to 0. So this is a very good tool, okay, that you could use. Once I finish, I will put it on Avenue to learn, play with it. As I said, I really want to inspire you by knowing the math, and then you can make decision on what you can do in your engineering design. So mathematics is critical down here. So over here, right, you can see that this is the function. Okay, so how is this related? So this is case number 1. If you look at case number 1, we have the mathematical expression, right? We have the, remember we had the mathematical expression. I hope to remember this. And the mathematical expression was x as a function of t, and this is equal to C1 E minus alpha plus beta times, then plus by C2 E minus alpha minus beta multiplied by pi, right? So that expression over there, where I highlight, so C1 expression minus alpha plus beta, so minus 4.36. And then you have C2. Okay, I better start recording first. I did. Okay. And then we have C2, and you can see the other side is a bigger number, right? Then from here, I put everything in matrix form, and then this is the graph that you see. Okay, so this is a not under dam, this is a over dam. Okay, over dam system. Okay, so to calculate the time of settling, okay, so at the end of the day, you have to solve this equation. Okay, you have to solve that equation over there. You all know how to solve the equation with your calculator? Yes or no? No, don't worry. On Monday, I will show you how to solve this equation with your calculator. Okay. So anyway, if I'm going to use Excel, okay, this is recorded. I think this is good to learn. So this expression over here, right, has to be equal to what? We want to find what is our time, right? So what we do is we go to data, okay? We go to what if, go seek. Okay, go seek means what? You want to get that this calculated value, which is the yellow highlighted equation. You want the whole thing to be equal to 0, and you're going to change your time. Okay, so it's like finding 0. And then all you need is press OK and go for beer. And now this is the solution. And you just put OK. So you see what happened? You see it shifted, yes or no? Right? Now, if I have both this graph, so this is case number 1, right? This is case number 2, right? Now, if I want it to be critically damped, okay, if I want it to be the structure to be critically damped, so i.e. I need the expression where we have c squared over here must be equal to what? Hey, how come I cannot click on my jiggy sort? Go on. Does it work now? Okay. So now what I want to do is I want c squared be equal to 4mk. So I want these two numbers to be the same. So what I do now, I can go to what if, go seek, okay? I want this number over here, which is calculated, to be equal to 25401.6. 25401.6. So now I want the structure to be critically damped, okay? I change my what? Damping coefficient, okay? And now I just put okay. Now you see the number is the same, yes or no? You no need to do try and error. Excel will help you do it. Have you all used this before, yes or no? No? Don't worry, it's recorded. You can learn. It's really useful to finding roots, okay? Any order, 6 order, 7 order, 8 order polynomial equation, you can find the solution, okay? So once you get over here, so now this structure is critically damped. When it's critically damped, right, the time to reach 0 become what? Shortened. Okay? So when that's the case, all I need to do now is I go seek, okay, and I want this number. I want this number. Let's say I'm going to change it to 0.5 first. Okay. Okay. Did I change something that I should not change? I'm going to cancel. My apologies. Okay. I'm going to put this as 0.5 first. Okay. So now, so if I put 0.5, you realize that he has not gone to 0 yet, right? So now what we do is I go to what if, go seek. Okay. I want this value to be equal to 0, and by changing this number over here. So the value that we get now is 0.838284. That shows the time for it to reach what? 0. Okay. Now, case number 2, right? Over here you can see case number 2. The expression, and a student asked me over there, why is it T? And I say I have not a clue. I just apply the formula. Okay. You will learn that in math. But the expression over there, this will be equal to C1 plus by C2T E minus alpha E. Right? So case number 2, this is the expression over here. So when I plot them using Excel again, right, the answers are very what? Very similar. Are we clear? Why similar? Because if you look at the calculated time to reach 0 is 0.847. Over here is 0.8382. Okay. 0.847 is 0.838 seconds. I think I will take a longer time to fart than that. Are we clear? Sorry, I have very dark sense of humor. My wife always tell me that, but I should not say that. But anyway. Yeah, I don't believe in putting a mask in front of you, but there you go, okay? So I will program it to do under dam and undam, and then I'll pass it to you on Excel. Play with it, okay? I want you to really visualize what is going on. And I want you to embrace this. Don't just look at it as just, it's another equation, okay? Have fun. Engineering is fun, okay? Not boring, like some arts program, but anyway. That's my sense of. Okay, stop having those dark humor. Right. So Interesting. Hold on. You know what's the funny thing now? I don't know where's my pen. Wait, it is somewhere, okay? And please. Yes, found it. Okay. So now, I'm so excited. We are going to do an example. Okay. So we're going to start a new example. Okay. And this example is for undamped system. Okay. So for undamped system, if we're going to sketch this out, this will be our spring only. And at a spring, let's say with the spring alone, okay, this is how the structure look like. Then we're going to put a load. And when we put a load, the spring get longer. It's an extension. Okay. So given to us that the displacement over here, it extends by 0.1 meter. Okay. So given to us the weight of the load is equal to 89 Newton, and the X is equal to 0.1 meter. Okay. So what we're going to find is we're going to determine the relationship between time and displacement of the load. Okay. So if we look at the characteristic equation, over here, the general form is m d squared x over dt squared plus by kx is equal to what? Is equal to 0. If I were to write the other expression with a damper, okay, when it's a damp, right, you have m d squared x over dt squared plus by c dx by dt plus by kx, the whole thing is equal to 0. For the undamped, what will happen is this has been dropped, as you can see on the left-hand side, right? So the next thing we are going to do, the standard procedure for solving an equation like this is, remember I told you that we have to check our c squared for mk. So we're going to check. Okay. So check c squared is equal to what? 0. Right? And then we know that 4mk is not equal to what? 0. But we have to determine the value of 4mk. Okay. So for now, we know that what we're going to have is we're going to have complex conjugate roots. Okay. We know that. Okay. Before we go on, we have to determine M and K. So M is easy. M is equal to 89 divided by 9.81. So this will be equal to 89 9.072 kilogram. Okay, and we can determine the stiffness K is equal to, so how we determine stiffness, right? When we put the load of 89 Newton, the spring extend by what? 0.9. Okay, so 89 divided by 0.1. So this is equal to 890 Newton per meter. Okay. So from here, we can compute what is our 4MK, right? So 4 multiplied by 9.072 multiplied by 890 is equal to, so 4 multiplied by 9.072 times by 890 is equal to 32296 or 32296.32. Okay.